Right. Right. So we're happy to have Nir Navon visiting us from Yale, where he's an associate professor of physics. He received his undergraduate degree from Université Libre de Bruxelles, then a master's from École Polytechnique, and then he got his PhD at École Normale. He then held a visiting position at the Weizmann Institute and a junior research fellowship at Trinity College in Cambridge. He has been at Yale since 2017. So he's a recipient of many awards, including the NSF Korea Award, the Sloan Fellowship, and the Packard Fellowship. His lab does groundbreaking work on quantum many-body physics with ultra-cold atoms, including, for example, far from equilibrium turbulent dynamics of quantum fluids, something I've been talking to him about and learning from him about recently. And today we will hear about some awesome work he's been doing on fermions in an optical box. So here we go.
All right. Good. So thank you very much, Alexei. So first of all, I would like to thank Alexei Mohammed for the invitation to be here. It's really nice. It's a very impressive and pretty intimidating place to be in. Lots of people know about quantum, so I have to be careful. Also, I understand that things are recorded, so I usually go on like aggressive tangent showing very preliminary results in my talks, but I completely took that out just to be very not take too many chances. But feel free to interrupt me during the talk. I like to be involved in discussion. And so the talk is going to be fermions in optical boxes. And one of the things that I like about the topic is that we end up covering quite a broad arrays of topics within physics, which makes it very fun because I end up learning lots of things. And after a few years, people think of me as an expert of something that I didn't know anything about in the few years before, turbulence being one of them. So it's just a very fun trajectory, and the platform, as I will show you, is a very versatile one. Experimentally pretty simple, but there's a lot of things that we can do with it. So yeah, here are like some of the cartoons of the thing I'm going to talk about. So hopefully by the end of the talk, you'll know what I'm talking about. So the first thing is I have 1 or 2 slides for motivation, but I feel a little ridiculous to talk about that here because I don't think that that's a crowd for which any motivation is needed as far as quantum simulation go. So let me do that in 30 seconds and get that very quickly through. So the idea is that are very interesting quantum phenomena that occur, for instance, at low temperatures or that involve collective quantum behavior. Conventional superconductivity, high TC superconductivity, or like more complicated phenomena that involve dynamics in neutron stars, pulsar glitches, and so on. So the idea is that you want to write simple models to understand those things, but very often even the simplest model of them, such as the Hubbard model or a famous model that's called fermions with contact interaction, which is one that I'm going to focus on in this talk. Well, there are lots of things that we cannot actually solve with any uncontrolled approximations. So there are some things that work very well. BCS Hamiltonian can be diagonalized in the mean field approximation, but there are many things for which, straight up theory is actually leaves us in a difficult position. So one of the things that's difficult about this system is to understand whether this model capture at least some of the physics involved. Apologies if that sounds a little childish. I'm sure many people are very familiar with those things, but just very, very quickly, challenges with real-world systems experiment is that very often systems are complex and it's not obvious what's necessary to understand the underlying behavior. There might be imperfections which can be very important for the physics involved. Very often, systems are not that versatile. You can tune interactions. You have to deal with very small length scale, very short time scales, which makes them sometimes hard to probe. And sometimes the systems are just very far, so it's hard to actually probe them. So the idea is you want to have a synthetic quantum system on which you want to actually implement this Hamiltonian very accurately. And this is the famous program of quantum simulation. So this has been booming in the past few years. Lots of people around here are very involved in these things. I don't need to tell, first of all, how exciting it is, but also how successful it has been in the past few years. There's been lots of different platforms that are used to pursue this kind of programs. And, ultracold atoms and molecule being undoubtedly the best of them. Yeah, that's the sort of joke I shouldn't do when things are recorded. But there are lots of different systems. It's just a very exciting topic. Now, one of the things that I really enjoy with cold atoms is the fact that we have a very interesting array of kind of physics that can be studied with cold atoms. And this is, again, goes back into this idea of like learning a lot of physics from our system. And many of these things were actually not necessarily anticipated from the start, but these days you can actually study condensed matter physics type or high energy physics, nuclear physics, fluid dynamics, and so on these ultra cold atom platform. So it's really a beautiful bridge to many areas of physics. And there are actually some spectacular examples of phenomena that were first predicted in other areas of physics, but measured for the first time with ultra cold atoms. And probably Efimov bound state might actually be one of the most spectacular example of things that predated cold atoms by decades, and cold atoms really added not just a new flavor, but really opened like completely new opportunities in those topics. For the local ones, I'm sure that you recognize, I used some of the local experiments here for some of these cartoons, so lots of activity all around, and here included. All right, so this is for a general introduction. Now let me talk a little bit more specifically about quantum gases in optical boxes. So this is something that I'm going to focus on in this talk. And one of the things that's quite remarkable about this development is that from a technical point of view, there's actually nothing that's particularly complicated. It's a bit funny that it took time to get there, but from a technical point of view, these are actually, by standard of our field, fairly easy experiments to do. And I think that for a long time, it was a little bit underappreciated how much these boxes allow really to clean up, not just quantitatively, but even qualitatively, provide some new way of looking at phenomena and unveiling new things. And so we wrote a few years ago with Zoran and Rob a review in Nature Physics, which is very nice bedtime reading. It's really very easy to read, and it's very quickly getting outdated, which is very nice because it shows how lively it is. And so here I'm showing a gallery of all sorts of uniform 3D uniform quantum gases that have been produced in the past few years. The field is about a decade old now. The first experiment was done in Cambridge. And you see that things have popped up everywhere, bosons and fermions in all sorts of dimensions, now also molecules. And it has really been a proliferation. I probably can't keep track of all the places that now increasingly use box as a tool. It becomes more and more routine in order to do many body physics in cleaner environment. And so essentially, again, I wish I could tell that there's some magic trick, but there's actually not really any magic trick. Most of these experiments are like blue detuned light. So essentially, the only thing you have to do is to draw the boundary of the box. And then essentially, the box itself is the dark part of the potential. So it's kind of like a very colloquial way of saying that is, it's a lot easier to make nothing flat than something flat. And what's flat here is the dark background. So these things have been done with liquid crystal SLMs, with digital micromirrors, and fixed optics. So again, from a technical point of view, it's actually relatively straightforward.
Okay, so there's no magic, but nevertheless, it's true that people tried earlier and they didn't succeed.
Yes.
So what's the story?
Because they were not good enough. I have to delete the recording after. Yeah, it's actually really a great question. And I think that I'm not completely familiar with like the whole history, but there was actually back in the late 90s and early 2000s, a lot of like painting with scanning AOM where people have tried to do that. And I'm not really sure like what was really, the technical issue about whether there was the time averaging lead to some heating. I don't think that there's anything that people would say like that was a showstopper. My hunch, really, at the end of the day, is that I don't think that people appreciate how interesting it would be and the motivation to actually push that forward, which is actually pretty impressive. I mean, it's not as simple as it sounds, because the first time that some of these experiments came out, I mean, referee reports were actually not so nice. I mean, some of them were not so nice to read. I mean, people say like, oh, it's a very nice textbook experiment, but really you're like redoing experiments that were like predicted 90 years ago. It's not that interesting. And I think that it took a little bit of time to appreciate that this would become a tool to do more new thing than just, 1995 BC in a box, so to speak. So I don't think it's technical. I really think that if you had told people back in hindsight, like things would be that great, my hunch is that even with painting, people who do that. I think that one big important step was really to avoid painting bright light. I think that making something flat, like making the light flat is just a pain, where just creating the boundaries is.
Sure, but people did try dark boxes and.
Yeah, there were billiard and things like that. I don't really know. I think that they might have had, you know, the extra conviction that things would lead to there, but yeah, it's a good question. We'll do some archaeology of that. So these were among the first experiments. Many of those experiments were really just showing basic quantum statistics. You know, the kind of like physics was actually already well established. But what's really amazing is to see all the different advantages that these optical boxes have. And just to show you a little bit of a broad classification, well, actually, before talking about the classification, maybe for people who are not so familiar about physics in optical boxes, let me maybe go back to like the simplest example. About the importance of being uniform. And so you'd say, well, everyone knows historically the harmonic trap have been the workhorse of ultracold atoms, because if you don't do anything special, close to a minimum, your trap by default is going to be harmonic. But the lack of translational invariance can actually be the lack, or translational invariance can actually be a game changer. And probably the simplest example to see this is Bose-Einstein condensation, which some people in the audience might be familiar with. And so just to take some prehistoric examples, you actually see that back in the days when people did these experiments in the mid-90s, it was actually not textbook Bose-Einstein condensation. You could see the transition both in momentum space and in real space. It's very easy undergraduate statistical mechanics to understand why, because the BC wave function and the thermal density have different sizes, both in the box or in momentum space. Here I just assume that it's non-interacting to simplify, but it's very easy to understand why the transition can actually be seen both in real and momentum space. When the first experiment was done in optical box, it was qualitatively very different. You could actually see that the transition, if you were measuring things in situ, there was actually no signature of the transition, but then you switch off the trap, let the gas expand, and then you see the transition in momentum space. So this was really a beautiful illustration about how qualitatively different things can be. The analysis is also very simple if you just assume that it's an infinite non-interacting system. Basically, it's homogeneous in real space, both for the BC and the thermal density, but the signature in the shape of the system in momentum space is very different. So this is well-established physics. It's all well known. Now, what's interesting is that you can actually use these tools to do things that are a lot more complicated. And it essentially goes along three lines, I would say. It's kind of a bit of a personal classification. And I have to say that even though it's about 10 years since these boxes have appeared, in many ways it feels like we're quite at the infancy of the topic, because many of these things have not been very, very well exploited yet. So probably one of the most exciting prospect is exploring phase diagrams. So if you're interested in studying complicated phases that might be very fragile, in a harmonic trap, you're essentially scanning the chemical potential in the trap if you look at things from a local density approximation point of view. And then fragile phases might be very, very hard to see because they occupy only a small shell in the system. So you want to create a uniform system in order to put the entire system in a given phase. Now, there are actually even deeper problems. If you want to study, for instance, long-range critical fluctuation, the density variation can actually be a serious showstopper. This is kind of a more qualitative argument. There is more of a quantitative one, which is that if you want to study density-dependent physics, which in many body physics is really ubiquitous, then in a trap you have inhomogeneous broadening because locally the density is different. And so when you take global measurements, then you average over all these local densities. And ever since people have started doing spectroscopy in this uniform system, people can really see much sharper feature than before. So from a quantitative perspective, it's very nice. And again, you can end up looking at things more carefully. And then again, from a more qualitative perspective, and something that I've been quite involved in, they are really just easier to interpret, experiments that are easier to interpret. So if you're studying, for instance, quantum dynamics, far from equilibrium dynamics of a quantum system, having no spatial dynamics due to an inhomogeneous trap can actually be a serious game changer. And again, in turbulence, for people who are a little bit familiar, most of the interesting dynamics occur in momentum space. But in a trap, there is a coupling between momentum and real space dynamics. And so for many of the experiments we did, they would have been basically impossible to, or very difficult to do in a harmonic trap. So the box really simplified things to the point where even a simple system like a rubidium BEC, which is weakly interacting, no quantum fluctuation, if you put it far from equilibrium, the dynamic is not trivial. Analyzing the experiment in a harmonic trap, I don't think that people would have really gone anywhere doing that. And so ever since, there's been some really spectacular results in this kind of community of people working on these experiments. Some of them more qualitative, some of them more quantitative, but I'm showing here a very, very biased selection. This is not exhaustive by any stretch, but there have been actually some really beautiful experiments discovering actually new solutions called dynamical breather in the group of Jean Dalibard, some very nice recurring dynamics of an expanding BC from a sharp edge trap. There's been some very clean RPES experiment in uniform system for which the homogeneity was also a very important experiment. Recently, there's been a revival of sound experiment, again, because studying sound in a homogeneous system with sharp boundaries is just so much nicer and cleaner than what could have been done before. I mean, don't get me wrong, like I sound like I'm trashing people from the past. Like things do take natural evolution and these experiments were pioneering, but over time, it's very nice to have all these improvements that just lead to experiments that are cleaner than what could have been done before. And also some really nice vortex dynamics and turbulent experiment that were just a lot easier to interpret in a harmonic trap. So this is really a selection, a very biased selection about what has been done, and things are keeping on this track. So the system that I'm going to focus on more specifically is the case of fermions with contact interaction, which doesn't sound maybe necessarily like all that sexy topic because it's quite an old one, but it's pretty amazing when you look at things carefully, how much you realize that many things have been missed, and in particular, pretty serious things. So from a theorist perspective, the model is almost the simplest one that you can write in a continuum. So you take fermions with a spin sigma with contact interaction. So you have just have a kinetic energy and an interaction energy, which is a contact interaction. The coupling is between two different spins because of Pauli principle. And you end up with S-wave scattering lengths between the spin sigma and sigma prime. And then you notice that there is no trapping potential here. We worked very hard to get rid of this. So now there is no trapping potential anymore. And despite how simple this Hamiltonian is, there is actually a lot of richness to it. There's a lot of things that you can study, in particular interplay between superfluidity and strong interaction if you increase the scattering length. There's a lot of few fermion physics that's actually not well understood. If you look at the normal phase, this is actually a prototypical Fermi liquid, one of the cleanest one actually, from which you can work things out from first principles. And you can actually study also very pure textbook quantum statistical phenomena. So just to go a little bit more in detail, let me break that down into, say, 3 subsets. Again, I'm not being exhaustive, but I'm just picking examples that are going to be useful for later. There is the attractive spin 1/2 system, where you just have up and down spin and one S-wave scattering length. The scattering length is 0 between up, and down, down. This is a very famous system because this is the system that holds the BCS crossover, which is the one where you can study the crossover between fermionic and bosonic superfluidity within a single system. Now, there are like maybe a little bit less known system. Now, if you look at the positive scattering length sector, but in a region where there are no molecules, so not at the molecule, not the molecular branch, but the upper branch, which is actually repulsive fermion, then you have what's called the repulsive spin 1/2 Fermi gas. And that one is very interesting because it's a prototypical Fermi liquid, and there's been some speculation of ferromagnetic physics that presumably could exist in that system, even though this is a pretty debated topic. And then you can actually study higher order fermions, for instance, what I call spin 1 fermion, even though the high energy colleague throw tomatoes at me when I do these things, but it's basically three component fermions for which there have been prediction of interesting and more exotic pairing patterns. Now, just to give you a little bit of a rundown of how we do that in my group, Nothing particular to be proud of. It's actually experimentally pretty simple, again, by our field standards. So the way we do that is after some routine cooling techniques, we go from a stainless steel chamber into a glass cell just to have a higher optical access, and then we end up with a fairly simple optical setup to create these optical boxes. So we have two possibilities. We have a set of axicon that allow to create a tube along one direction. Then we have two DMDs that allowed us to create spatially dependent potential along two orthogonal directions. This is actually quite simple. We're using, for those who want a few more technical details, we're using blue detuned light, which is 639 nanometer for lithium 6. Something I'm not going to talk about, but it's actually pretty important when you discuss boxes, is that gravity exists. Something that most people tend to forget. It turns out gravity is actually pretty large at these energy scale. And it's very easy to forget with a harmonic trap, because in a harmonic trap, a parabola plus a line is a parabola. So when you have all that gravity does is just displacing a harmonic trap. Now, the problem with boxes is that to zeroth order, a box is nothing. So anything that you have becomes your dominant potential. So you have to be pretty careful to cancel any residual forces in all directions. So this is actually pretty tedious. So we have sets of coils to actually align our Feshbach field to the levitation gradient. So we're doing that magnetically with the using the magnetic moment of the atoms. But the bottom line is that once you know how to do that, once you've done it, it's easy to do. And so at the end, you end up with like really beautiful picture. You know, when you've been old enough to work with the harmonic trap experiments, then seeing this picture of uniform traps are like just really beautiful. So this is a cylindrical potential. So you see this is along the line of sight. So it's a semicircle when it's integrated along the line of sight. And then in the other direction, you see that it's a very flat. And it's essentially, you know, in our best images, it's about 1 pixel sharp on the camera. So in our case, we're not actually looking at making these things as sharp as possible, because we're looking at 3D boxes. So there is a depth of field issue that you have to be a little bit careful about. And just to throw maybe a bone at Bill, if you might be interested, one of the questions that's very interesting is like, well, how good are these boxes? So this is a little bit of a can of worms, so I'm going to leave that aside unless I get a question about that.
Well, I'll ask a question, but not about that.
Okay.
So as you said, you know, once you've done it, it's easy. That's true of everything.
Yeah.
But is there any case to be made for doing these kinds of experiments, say on the space station?
Yeah.
Because gravity is a whole lot easier there, but on the other hand, it's pretty expensive to get there.
Yes, it's a good point. So there are some arguments about that. I would say that the one that I find the most compelling from a quantum many-body point of view is the issue of mixtures. So for instance, all these things work as long as you're levitating something that has the same magnetic moment, or if you're using light, you know, susceptibility has to be close enough. If you want to have, say, different mixture with different masses and stuff like that, 3D boxes on Earth is a, you know, it's a showstopper. So for this sort of thing, I would say like space would definitely be a good argument. There's also about making large volume systems. There's actually some interesting point that at this level are not technical issues at all, but the fact that we're using magnetic fields to compensate, it turns out that Maxwell equations have some built-in constraint to them. It turns out there's only so much you can do with them. And so when you actually take a gradient vertically and you compensate for that, then you end up with an in-plane curvature that's unavoidable. And it's actually this in-plane curvature is 1 over the bias. So when the bias is large enough, it's fine. But if you want a large volume box, at some point you're going to hit a roadblock. And so for those things, in this case, lithium is very nice because it's light and the Fermi energy is so high that you get that for free. I mean, lithium is very annoying for other reasons, but for that it's good. But again, from a more fundamental perspective, it goes into a very interesting direction, again, of how good these boxes are. For everything that we've done so far, the flatness of the box and the sharpness of the wall are good enough. At some point, when we'll start to do increasingly more complex quantum many-body physics, characterizing these boxes will become more and more difficult. And for all these things, how homogeneous the box is going to be will become increasingly more important. So far, it's a little bit of like a dirty secret in the business, like people are sweeping that under the rug, which is fine for now, but probably in the near future, many of those issues are going to become more serious. Yeah, thanks for asking. Other questions? All right. So this is a cylindrical potential. So you see that this is actually pretty nice. Now you can actually, now that we have these DMDs, we can actually control with much more versatility the kind of potential we can make. And for all these years that I started reading these theory papers that always start with, well, let's assume a quantum gas in a cubic box of size L by L by L that nobody was close to doing. Well, these days we actually can do these kind of cubic boxes. So it's just very nice how we're catching up. Not periodic boundary conditions yet in 3D, but you know, there's still we're getting better. But just to tell you that you know, many of those technical roadblocks are really falling one after the other. And obviously, you know, the versatility of these tools is really pretty amazing. You can do things that are even more scientific than that, like sending stuff to the PR people in your university, and they just are happy paying $1 million for a machine that can write Yale with ultracold fermionic matter. So this is all about static. There's a whole different story I'm not going to talk about at all, is that this device is actually fast. So some of the things that we're discussing with Alexei and Mohammed actually is how to exploit the time dynamics that these devices allow to do even more versatile, controllable thing than the things that we've been doing so far. All right, so now let's show me a gallery. So how much time do I have? Okay, great. So this is the moment where my speech pace is going to double. So since it's recorded, you can always run it in half the speed later. So this is a gallery of the things that we've been doing in the past 2-3 years or so. It's been very fun because a lot of these things are a lot of different physics. I'm not going to have the time to talk about everything because each of these topics would easily take 45 minutes, like a whole seminar. But I want to try to give you a little bit of a taste of these things, and many of those things are orthogonal. So I'm going to shamelessly oversimplify some things and cherry pick some subsets of results. But I encourage you to look at the papers if you're interested, and at least give you a little bit of a flavor of the things that we're doing at the cost of some of the depth. So I apologize for that in advance. But let me very, very quickly go through the kind of experiments that we've been doing. So our first experiment was actually studying the three-body recombination dynamics of spin 1/2 fermion, of repulsive spin 1/2 fermions. So this was kind of recovering an old result, 20 years old experiment, result that hadn't been checked before. So this was actually not that surprising. It was a neat experiment, but the result was actually quite known. Here we actually studied the recombination dynamics of a 3-component Fermi gas, and this is actually something I'm going to talk about more, because we actually came across a major surprise, and many people, at least not in our field, not in ultracold atom, sometimes criticize cold atom experimentalists as saying that we do experiments for which we know the results in advance. Well, this is actually really an example of something where we really didn't know at all. I mean, I didn't even think it would be interesting before doing the experiment. I'm going to talk also about this measurement of the fermionic Joule-Thomson effect. So again, it's a pretty fundamental result predicted a long time ago. And then I'm going to briefly mention some parts of this work, which was the observation of the emergence of sound in a shaken Fermi gas. At the very end, I'm just going to flash in one slide how we tune the properties of Fermi polarion with an external RF field, and then a work that we put on arXiv 1 month ago, which I really love, about studying actually how Fermi golden rule emerges in the study of a quantum many-body system. So it's, again, a pretty fundamental topic that was not something that we were aimed at in advance, but we got dragged into and was pretty exciting. So this is like the general gallery. Now let me focus a little bit more about the things that I'm going to talk about here. So I'm going to take a little bit less than 10 minutes per per topic. So again, pretty superficial, but at least you'll get a taste of everything. So I will start with this Joule-Thomson effect, how we came from verifying a 90-year-old prediction to measuring for the first time the Leonhardt response, which is a celebrated 70-year-old textbook result in condensed matter. And then these were actually, again, well-known, well-predicted, to something that was really not predicted at all. All right, so let me start with the fermionic Joule-Thomson effect. So maybe for some people who have a few years behind their last thermodynamics and statistical mechanics class, let me remind you very, very quickly what the Joule-Thomson effect is about. It's actually a fundamental process in thermodynamics where the way that it's presented in textbook is that you take a mole of a gas and you throttle it through a porous plug. And in that process, where the system is actually isolated from the outside, so there is no heat exchange with the outside world, you can actually show that from the initial to the final state, what is conserved from the two compartments is the enthalpy of the system, which is the internal energy plus PV. And so there is no heat exchange with the outside world. And the basic question of the Joule-Thomson effect is, how does the temperature changes given a known change of the pressure between the left and the right side? And this has been an absolutely critical topic, not just in fundamental physics, but also in practical, because it was one of the phenomena that allowed the liquefaction of gases and the birth of modern cryogenics. So it's a very historically very important topic. And it's pretty simple to appreciate that the main quantity of interest in this process is called the Joule-Thomson effect, which is quite intuitively how the temperature changes when the pressure of the system changes at a fixed enthalpy. So depending on the sign of the Joule-Thomson coefficient, you could have cooling or heating. And you can actually verify, it's an elementary exercise, that if you take an ideal classical gas, equation of state, then the Joule-Thomson effect is 0. There's no Joule-Thomson effect in an ideal classical gas. Now, if you actually introduce interaction, it's pretty amazing, even in classical statistical mechanics, how the Joule-Thomson effect is remarkably rich, and you end up with non-trivial Joule-Thomson diagram for typical molecular gases. So this is a temperature and pressure diagram. And actually, this comes from the fact that typically in intermolecular potential, you have both long-range attraction and short-range repulsion. And depending on which part of the potential dominates, you can actually either have cooling or heating for the Joule-Thomson effect. So you have whole region where you have cooling, and then you have what's called an inversion curve. And then outside of that inversion curve, the system is heating. But the key point of the Joule-Thomson effect, the classical Joule-Thomson effect, is it's non-trivial only owing to interactions. If there are no interactions, then there is no Joule-Thomson effect, and you can actually learn a lot about the interaction of a system from this kind of diagram. Now, this was known since the mid-19th century or so. There was actually, if you like physics archaeology, there's some nice Nature paper from 1937, back in the days when you could write a Nature paper in 1.5 column. That's appropriately titled Joule-Thomson Effect and Quantum Statistics. And actually, not so long after the birth of quantum statistics, some folks actually realized that quantum statistics and indistinguishability gives rise to a Joule-Thomson effect alone without the need for any interaction. So it's really quantum correlations that give rise, that essentially mimic interactions and give rise to a non-trivial Joule-Thomson effect, which is the quantum Joule-Thomson effect. Now, this was actually known, and I actually worked in Cambridge with Zoran and other on this experiment for bosons, actually about 10 years ago. And we actually observed for the first time the Joule-Thomson effect for bosons, which is a heating. So there is this thing about fermion attract, that you always learn not to believe. Turns out, as far as the Joule-Thomson goes, it works pretty well. And maybe just to go a little bit into technical, but there are lots of subtleties that I have to overlook. But the way that we realize this Joule-Thomson process is not by a throttling, but by a rarefaction. So we essentially take this gas of atoms, and the density goes down, but it goes down in a way that preserves the energy per particle. And when you have a universal relation between the energy and the product of PV, you can show that the energy per particle being conserved is the same as the enthalpy per particle being conserved. So one implies the others. And if you have this, which actually applies both to ideal quantum gases, both fermions and bosons, and it turns out also to the unitary Fermi gas, then the Joule-Thomson effect can actually be mapped into this Joule rarefaction, and the Joule-Thomson coefficient is dt by dn at constant h. Now, this was done about 10 years ago, but the effect was actually never observed with fermions before, and so you can guess where I'm going with this. So we actually redid this experiment with fermions, and the gist of the experiment is again pretty simple. And it was actually even predicted explicitly that the Joule-Thomson expansion would produce a heating effect for Fermi-Dirac statistics. So the effect is opposite for bosons and for fermions. So just a tiny bit of technical. The two things that you have to be particularly careful when you do this experiment is to achieve an energy-independent rarefaction, which, again, I'm oversimplifying. There is quite a few things to be careful about, but the point is that we wanted to have vacuum-limited lifetime for the gas, but you also want the gas to be thermalized, so you need enough interaction to be thermalized, but sufficiently weak interaction so that you can wait for a long time without having any losses due to a residual evaporation. But the point is that we can tune A and guarantee that these two conflicting conditions could actually be verified at the same time. And then you have to be able to measure the temperature, which in this case, if you deal about the ideal or the near ideal Fermi gas, this is actually a trivial problem because you can just do that in time of flight. The interaction KFA is very weak, so the effect of interaction in flight is negligible, and you can just do that the way it was always done. So now you actually put these two things together and you can measure how the temperature changes as the system rarefies and put that on the whole plot. And then you actually end up with the observation of the Joule-Thomson effect. So this is the atom number over the initial number divided by the temperature over the instantaneous Fermi temperature. And so you see that we started at initial T over TF here. There are like three series. And if there is no Joule-Thomson effect, you would have these dotted lines. Now, these dotted lines are really trivial because the TF here is proportional to the density to the power 2/3. So when the system rarefies, T over TF goes up, even though the temperature doesn't change. But this is basically your classical baseline. So this will tell you when there is no Joule-Thomson effect. You see that the data is well above that. So there is actually quite a bit of excessive heating. So if you actually do a very simple estimate, just taking ideal gas theory, which is really undergrad physics, you end up with these solid lines. So you see that they're actually pretty close to explaining the data, but there is actually a little bit of a residual heating, and it took us some time to appreciate that this was actually due to the residual heating in the box, which is actually a very, very small heating. It's about 200 picokelvin per second of heating at the best of what we could stabilize. And if you actually take this residual heating into account, you actually get this dashed line. So we did a variant of the experiment where we didn't have to wait that long to actually get rid of this residual heating, but just for the sake of speed, I'm not going to show this. So this is really the first observation of the fermionic Joule-Thomson effect. Now, to go a little bit on the interpretation, there's actually some very neat way of interpret this, both at low and at high temperature. And they're actually they quite demystify the physics. At low temperature, this is nothing but Fermi hole heating, actually. So if you're taking a T equals 0 Fermi gas, and you want to have a rarefaction that conserves E over N, then you're going to poke holes into the Fermi C, and by poking holes, you're going to increase the temperature of the gas, and this is going to lead to a low heating, because there is an excess energy, EF minus E, that you inject every time that you actually peak every time that you remove an average energy E. The only way to keep the temperature constant, obviously, would be to remove the atoms that are on the edge of the Fermi C. But E over N being constant means that they're not doing that, and this actually leads to this residual heating. At high temperature, there is another neat interpretation for that, and this actually comes from calculating pair correlations in quantum gases. And in the virial expansion, if you're just looking at two-body correlation, there's actually some very nice, and again, it's very, very nice, very simple physics to do. You can calculate the pair correlation function with at high temperature, looks like this 1 plus minus this Gaussian divided by the thermal de Broglie wavelength. And the sign plus or minus is actually depending on whether you have bosons or fermions. Now, classically, this pair correlation is very easy in the virial expansion and calculated to be proportional to the interatomic potential. So if you have U being the interaction between the particles, then the pair correlation is just the exponential of minus beta times U. So now a funny game that you can do is to define an interaction quantum potential between non-interacting quantum particle. So this sounds a little bit like piracy, but it actually and it sort of is. So you define this U quantum as the log of this pair correlation. So now you have an interaction potential between quantum particles, and then you see that for fermions it's a repulsive potential, and for bosons it's an attractive potential. And it turns out that at the highest virial order, meaning two-particle correlation, this actually quantitatively gives you the correct Joule-Thomson effect. So all the time that you're always being told that bosons attract and fermions repel is a lie, is a convenient lie, it turns out that actually in the virial expansion, this is actually quantitatively accurate. So you can actually understand that in that way, and it gives you the right result.
So is another way of saying this is that you're, in the high T case, you're poking a hole in the pair correlation function, and then the temperature is a response to that?
Yeah, so it's probably a little bit less useful to see that, because essentially it's almost a classical gas, but you have just the residue of interaction. So the better way to look at that from the high temperature perspective is to look at the equation of state from a virial point of view. So if you look at high temperature, you'd have the ideal gas, and then you would have correction in power of the fugacity. And so if you actually take the lowest correction in terms of the fugacity, this is the lowest influence of quantum statistics on the thermodynamics. So I think it's more useful than to look at that in terms of holes, because there is almost no Pauli blocking at high temperature. All right, so just to finish on this, it's actually pretty funny to look at the end of the paper, where they prophetically said, it therefore seems possible that the Joule-Thomson effect under suitable condition may provide an experimental test of the statistics obeyed by gases, say helium. So it does work. We confirm that lithium-6 is a fermion. That's all right. That was for one. Alexei, how much time do I left? 17. Okay, not so bad. All right. A whole part that I'm completely leaving aside, which is actually a really nice thing that we also studied, was the Joule-Thomson effect in the strongly interacting Fermi gas. So you can actually tune the scattering length to infinite and study what's the so-called unitary Fermi gas, for which everything is more complicated, because guaranteeing that it's a Joule-Thomson rarefaction and doing the thermometry are a lot more complicated, but we actually also managed to do that. And the Joule-Thomson effect is a lot more complicated, because you actually need to solve a complex many-body problem to determine what is the Joule-Thomson coefficient in that case. So just for the sake of time, I'm going to leave that aside, but I encourage you to look at our work if you're interested. All right, let's
Sure you're not on the 40-minute Zoom?
yeah, that'll be a cruel way of limiting the time of the speaker. Thank you. All right. Okay, so again, there's a lot of things to talk about this. The paper is actually going to come out in PRX very soon. I'm just going to scratch the surface and give you a little bit just of neat bits and pieces of this work. And again, just sort of tell you how interesting it is that we're revisiting much of my business. It's a little bit dirty and shameful to admit it in that way, but a lot of my business relies on revisiting old experiments that people have done in the 90s and early 2000s. And when you do them in a box, you just see that lots of things actually happen to just lots of things that we thought we understood actually does more details, and actually pretty important one to uncover. And maybe this is another one of those experiments where it's amazing how the box just unveil new things. Yeah.
Click on it.
Yeah. All right. So again, a little bit of archaeology for people who remember the graduate condensed matter classes. It actually starts with a very simple question, which is what is the density response of an electron gas to an external perturbation? This is a textbook calculation that was done by Jens Linhart in the mid-50s. It's actually a classic result where he calculated the dielectric function and used the famous random phase approximation to take into account the interaction, from which you can deduce a lot of interesting physics, charge screening, plasma oscillation, and so on. But along the way of this calculation, he actually calculated for the first time the density response of an ideal Fermi gas. And this is a result that's called the Lienhardt function, or the Lienhardt response in this result. And it's really a beautiful calculation that's not so trivial, even though we're talking about ideal fermions. But the basic setting is very simple. You take a Hamiltonian. So in this case, it's the free fermion Hamiltonian. You had an external potential that couples to density. So it's very simple. Here, this is the field operator for fermion. I'm not using any spins here because I assume it's a spinless gas. And then I use an external potential. And then I couple these atoms to this external potential and look at how the density of the system responds to this force. If you look at things from linear response point of view, so for small drives, there is a direct proportionality between the density and the drive. And in Fourier, things become very simple because they're very local, both in space and in time. Then you have the wave vector Q of the excitation and the omega of the excitation. And from that, you can actually get an analytic result for the susceptibility, the response function, the density response function of the gas to this external perturbation. Which is actually this expression, which you can actually calculate analytically in the zero temperature limit. I'm going to a little bit narrow things down because in our case, which is maybe a little bit unusual for condensed matter people, we're going to look only at the long wavelength limit. So when Q essentially is as large as possible, which is 1 over the system size L. And then if you take this limit, you end up with an exact result, an exact analytical result for the response function as a function of the frequency omega here. And so this omega naught here is the only frequency that you can build from the dimension of the system, which is essentially something proportional to the Fermi velocity. So it's the only frequency scale associated with the intrinsic property of that gas. So this is actually a very, very neat, elegant result. As far as I could tell, and I asked a few of my condensed matter theory colleagues, I didn't find anybody who ever claimed to measure directly the Lienhardt function in any other system. There are lots of dispersion relation and plasma mode and all these things that have been measured before, which are a direct consequence of that. But as far as I can tell, I don't think that anybody has claimed direct measurement of the Lienhardt response. And it turns out that with our system, we can do that in a very straightforward way. And the way that we do that experimentally is as follows. So we take our gas, which is in this case a 2-component Fermi gas, that we take in a box, we trap in a box just for convenience. And then we take our levitation field that acts vertically, and then instead of keeping it flat, we actually oscillate it with a certain frequency omega, which actually creates a spatially uniform force that oscillates as a function of time. And so you see that when you do this, and the drive amplitude is 0, so the driving potential is U sine omega t, multiplied by y, which is a vertical direction. So this is a constant gradient. And when you have a certain finite amplitude of the drive, then you see the density sloshing back and forth. And here we tune the scattering length so that there is no interaction between the two components, so that this is essentially like a single component Fermi gas. And that's about it, actually. Once you have this, then just from this density response, you can directly measure the Lienhardt function. So the way that we do that in practice is we very often actually look, rather than the whole density, we measure the center of mass of the density response, which is very easy to measure with a very high precision. And so when you look at, so this omega naught is what I told you about, which is the natural frequency of the system, Fermi velocity divided by L, and the center of mass of the density is just y multiplied by the time-dependent density distribution minus the background. And so you see actually, and there's a lot of subtle things to say about that, which I'm completely skipping under the rug, is that if you wait long enough, the system actually responds in the steady state. So it actually responds at the frequency of the drive, which for an ideal gas is actually not all that obvious where that steady state actually comes from, because there is presumably no dissipation in that system. But just let's take that for granted. The center of mass oscillates at the drive frequency. And then you see that the amplitude and the phase changed with depending on the drive frequency. And this is essentially the response function chi of omega. So you can actually put these things together. And the math is really straightforward. From the amplitude of the center of mass and the phase of the center of mass, you can directly relate to the real and the imaginary part of the response function at Q is equal to 1 over L, and at the frequency omega s of the shaking. And so you can either plot the amplitudes or the phase, or you can rather plot the real part and the imaginary part of the response function. And this gave you the first measurement of the Linhart response. And so you see that these three measurements are measurements at different temperature. The dashed line is the prediction at 0 temperature. And you can actually see that the response is actually pretty sharp, even at low temperature, which is a pretty intriguing way. I mean, I got pretty intrigued that this could actually be a quite sensitive thermometer at low temperature, even for the weakly interacting gas, which has been a notoriously non-trivial thing to do. But the bottom line is that you see that there is a very good agreement without any free parameters. So this is just ideal gas prediction, and things work very well. Now, again, just because I'm just completely out of time, I can't talk about a lot of the interesting physics, but there's some really neat geometric interpretation for this Linhart function. And in particular, you can actually deduce the 0 temperature Linhart function from a geometric argument about calculating the volume of available states for a displaced Fermi seed that conserves both the momentum and the energy of the excitation. And you can actually get this triangle, this Linhart triangle with this singularity edge at the Fermi surface. But just I'm running out of time, so I'm going to leave that aside. But there's just a lot of nice physics, even in a system that very well understood physically. But we actually didn't stop there. This is all well understood. You see there is no resonance. It's a broad density response. Now what we can do is, because we can tune interaction, here we can actually increase A, and then see what happens when you do this. And then when we do that, something pretty dramatic happens. So you see that the broad response of the Linhart response, which is a broad potato because it's essentially particle hole excitation, as you increase interactions here from orange towards red, you actually see that the response narrows down pretty dramatically. And then you end up with a very sharp feature and a very sharp dispersive feature for the real part of chi, which actually tells you that there is a collective sound mode that actually appears as you increase interactions. So this is known that if you increase enough interaction, at some point the hydrodynamic criterion is going to be verified. Omega multiplied by the mean collision time is going to become small, and then you can actually support a sound mode. Now, again, I'm going to cut aggressive corners here, but even for the weakly interacting system, it's amazing how non-trivial the physics is. And we had some collaboration with friends, colleagues in France that actually wrote down a first principle Fermi liquid theory. So actually a transport equation for the quasi-particle that don't involve any phenomenological parameters. So it's essentially there are no Landau parameters that are just parachuted from anywhere. Here, everything depends on microscopic parameters, which is the coupling constant G and the collisional integral here that involve only the scattering length. And so you have this what's called the RPA term, which is mean field interaction, and the collision, and the rest is a completely standard transport equation. So this is really from first principle. You're not making any assumption. To lowest order, the transport equation for the Fermi liquid should look like this. And what's nice is that we can actually compare the results when we increase interaction to this theory without any free parameter. And it turns out that solving this equation, even for weak interaction, is not a simple problem theoretically. But they did it, and we end up with a pretty nice comparison. So you see this is the response function, the imaginary and the real part, as we increase interaction. So you see how things narrow down and become sharper and higher. And the lines are basically this theory prediction from this transport equation, taking into account only collision, only mean field, and both. And you can actually see that in our regime of temperature, you have to take both into account to have a good agreement. And how to moderate interaction, the agreement is actually really good, given that there is actually zero free parameter in this description. So you see that this is actually pretty amazing up to this point. And then you see that you increase interaction further, and then it becomes pretty miserable. And then here you see no theory line. So you could say that the theorists are so ashamed with the disagreement that they don't show it. It's actually even worse than that. This theory is actually pathological. When you increase interactions enough, this is a low order, the lowest order theory, and you have a dynamic instability. So past certain strength of interaction, the theory actually is completely meaningless, so they can't even plot anything here. So we know phenomenologically that there should be hydrodynamic equations here, and we can write down the hydrodynamic equation with phenomenological transport coefficient. But the question is, could we actually learn some of these hydrodynamics, some of these things that I'm getting very interested with the local folks here to try to understand. But you see that if you really stick to your canons of first principle theory, the only thing that we can do so far is up to that point. But again, weak interaction, and it's already surprisingly not trivial. So you see an excellent agreement with our free parameter up to moderate interaction, and then things really break down at strong interactions for which there is actually no known first principle theory. All right. How much? Yes.
What's the size dependence of the prediction? Is this in the thermodynamic? Because you said you have a Q, which is like
yes, yes. So this is all for an infinite system as far as the theory goes. So it's a large system, but they don't assume that there's any subtleties from the fixed boundaries.
And your experimental result is roughly consistent with that?
Yeah, so this is actually a very good question. Like, well, or basically rephrased it, is how important are finite size effects in our system? I mean, I guess I could easily just say like, yeah, they're just not important. But I'm not sure that I really, and use a little bit of argument of authority, but I'm not so sure that I have such a convincing argument, because you would say, I believe that they're not important. Let's put it that way. I think that it's not so, I mean, obviously you could change the size of the system and see that things actually scale properly, which I believe is what we would recover if we did it. I don't think that there is much debate on that. But I'm not sure that I can really promise you 100%. I'm pretty convinced that that's the answer, that it's fine, but I wouldn't be able to say that we checked it carefully enough so that we can be sure of. There is a variation of that, which is actually very interesting, which is that these days we have relatively direct evidence that there is some residual small disorder in the bottom of the trap. And we're getting very excited in understanding how disorder affects sound, and go back to like Drude, and quantum, conductivity and so on in that system. I should not give all these ideas in recording. But the question is, well, how do we know that, for instance, all these imperfections are going to affect this? And the truth is, we actually don't really know for sure. What we have is basically that we have a certification problem. We have that here, the theory agrees very well with what we expect. So it looks like it's not that large. But again, I think that if we were more careful, I would be very interested to know how much, say, either finite size or disorder would affect, say, the Linhart prediction. So these are things that we're actually looking at right now. So it's not a trivial question, and I'm not sure I have a great answer either.
I try to rephrase it quickly. So what I understood, which is that you tried to vary the size, but in some sense a different experiment, and then you just have a different potential, and so you can't tell whether it's disorder or size, or?
Well, no. So as an experimentalist, I would change the size and check that when the the response is properly normalized to the size of the system, the result collapse as a function of the size. Kind of like finite size scaling, but experimentally. It's a lot of data, so I don't think that, and I don't think any one of us really worried that we have a finite size problem, especially that the size of the, actually we're getting excited at seeing effect of the fixed boundary on the physics, and it's actually pretty hard to see. So again, I can't promise because I haven't done that, but I'm pretty sure that if we did, the effect would be small. But it would be great. I think that if you took Linhart with finite size, with finite size effect, I don't think that the analytic calculation would be all that simple either. So very often, if you do these things, as soon as you drop one assumption, like the linear calculation is already not that trivial to start with. So, but yeah, it's a good question.
But now I'm curious, what's causing the disorder in the bottom of the trap?
Yeah. This is. I mean, as always, we draw the boundaries and then we say, as convinced experimentalists, the bottom is dark.
Yeah.
But it's obviously dark up to a certain point.
Scattered light.
Exactly, speckle and like whatnot. So obviously it's going to be dark up to a certain point. But again, that was the kind of stuff that people said like, yeah, it's not important. And then they looked the other way and that was fine. And again, it's not that we've done some quantitative experiment that allowed us to see that this was particularly unimportant. Actually, it's not that true, because if you change the depth of the potential, you can essentially change the strength of the disorder and see again some independence on that. But there is actually some interesting dynamic experiment when we see the establishment of a steady state. And for instance, if you take the ideal gas and you're driving along in one direction, we actually see that slowly energy leaks into the other direction, even without interaction. So it looks like something allows to scatter energy in other direction that usually would be interaction, but in this case, it's not interaction. And we actually think that this is actually scatter from the disordered potential. So it's guaranteed to be there. The question is, how high is it and how important is it quantitatively? And for that, we don't have great answers yet, but to be continued. Yeah.
Maybe here.
Yeah. Oh, yeah. Well, okay, great. So fine. So let me talk very quickly. Another 3 minutes, maybe. No? Oh, yeah, that's already too late. Okay, so we studied the attenuation of the system, which is also very interesting in the Fermi liquid regime. We mapped the quasi-particle distribution from the collisionless to the hydrodynamic regime, which is also something that you see in textbook drawn but never measured, which was actually nice to see that for the first time. Again, no time to go into the details of that. Let me, in a minute and a half, talk to you just about the essence of this mystery. Which was quite a big struggle with referees that couldn't believe that this was real, and I don't even believe that it's real, but it's just what we see. And so let me cut all corners. If you create 3-component fermions, it's a very nice system for quantum simulation and so on. There's actually a lot of the protection we had for spin 1/2 fermions that are no longer accessible for spin 1 fermions, and there is FMR physics and things like that. This was actually studied in the late 2000s by groups in Germany and in Japan. But a lot was actually not studied about whether you could have quasi-equilibrium or pre-thermal physics. And the homogeneous system was never studied. And in particular, the density imbalance gas was not studied. So now the question is, why is it interesting? And my answer beforehand would have been, well, it's just not interesting, actually, because we know exactly how it's going to behave. There was actually some other related work that actually came out this month. So experimentally, it's very easy to do because they have the same magnetic moment, so we can levitate all 3 components with one gradient. So we can create a lithium gas of 1, 2, and 3 components very easily. And then we can show that if we balance the density of the gas, no matter what is the magnetic field that we measure, we see that the gas remains always balanced and decay with the rate that changes with D field. It doesn't really matter, but we can actually measure in the box, which is very nice, directly that it's 3-body recombination. We see that n dot is proportional to n cube, which is completely unexpected because you have 3-component, 3-body recombination between spin 1, spin 2, and spin 3. And you can actually write down very easily what is the recombination equation. N dot J is equal to minus L3 multiplied by the product of the 3 densities. So this is actually really trivial, but it actually leads to a very strong constraint, which is that if you imbalance the system, then the rate of all 3 should actually be the same. So we actually imbalance the density of the 3 components, and you see that the absolute loss actually follows, is actually very close to being the same at a given field. So you say this is all trivial. But now you change the field, and then all of a sudden, all hell breaks loose, and you actually find some pretty basic breakdown of well-known arithmetics that you see 3-body recombination involving 3-component fermions, for which the rate of the loss of all 3 components is actually not the same. So you see that the majority actually lose more than the median than the minority. And the rest of the time that I don't have, so I have to continue on a different seminar, was actually how we tried to reconstruct experimentally this decay equation, which we managed to do heuristically. So we have a heuristic equation that described this. We did a lot of experiments to verify what about this process was simple, what wasn't simple. There's a lot of very interesting stuff I can't talk about. But here basically is the modified 3-body equation that involved a very weird prefactor here and involved an anomaly parameter eta that we just fit to our data, and that explains everything very well. Now, to make a very long story short, the question is, where does this eta come from? And the very simple answer is we actually don't know. So we have this data for almost 3 years now, And essentially, all the testable hypotheses that came across to explain this either fail qualitatively or fail quantitatively. So there's been ideas of quantum correlation, of avalanche losses, or evaporation in a dense medium that were advanced to actually explain what it was, and no quantitative plausible explanation has survived the test of the experimental data. And I didn't expect anything wild to happen in that system. And then we have this nerve-wracking data that we don't manage to explain, and apparently nobody else managed to. All right, so let me, so there are a lot of strongly constraining experimental statements we made about this system. So it's actually well established experimentally. We just don't know where that comes from. So some referee would say, well, I believe it's some stupid technical thing, which I sort of, it's actually possible, but nobody seems to be able to say what kind of stupid technical thing that would be, which would be able to test. So it's actually a pretty interesting and pretty stressful situation. All right, I didn't have the time. I don't have the time on top of not having the time to talk about this three-body recombination experiment we did, some interesting numerical work that we did on the equation of state of turbulent Gross-Pitayevsky model. This Fermi golden rule experiment that we put on arXiv last month, which is how you can see Fermi golden rule appear experimentally as you probe the system. If you have questions, I would be happy to talk about this more. This driven polaron system, which also is very nice, how you can tune the property of quasi-particles with an external field. And I think that's enough. And with that, I would like to thank the people involved in this experiment and you for your attention.
Question.
That was a bit of a dash.
A silly question, but show these nice like box potentials,
Yes.
a cylindrical drum, sort of in maybe a cubic box. So, what's the limit on that? What kind of shapes can you
Sky's the limit.
think about?
Well, I mean, in 3D, you have like the
Cylinder?
yeah. I mean, yeah.
Is that a picture? Yale? Is that a...
Yeah, so Yale is like along, like, is actually, along the direction of propagation. So you have a little bit of like, diffraction limit involved and in propagation and things like that. So in 2D, somewhat a little cleaner because you don't have a line of sight issue. But as far as 3D dimension, we have two axes. So there's actually quite a lot that we can do. So the things that I haven't shown, but we're getting very excited with Alex and Mohamed to work on is especially these strongly interacting gases have phenomenological hydrodynamic equation to describe them, but nobody knows from first principle how to derive them because it's too difficult to go from the Hamiltonian to hydrodynamic. So what we can do is to create time-dependent flow when you have different geometries and time-dependent evolution, where you can actually study flows of a system for which you want to learn the governing equation. So it's not just that the geometry is versatile, you have also quite a nice degree of controllability on time. So all of these things have caveat on diffraction limit and like various things that might become a problem at some point, but it's an amazingly versatile tool. Like there are really lots of things that you can imagine doing before hitting a brick wall at some point.
Very idealized,
Yeah.
but realized.
Exactly. No, it's a lot of fun. I mean, the machine is outputting pretty much like faster data that our brain can process it. So it's a pretty frustrating place to be in that, but that's a good place also.
Yeah, let's thank you again.